A very warm good evening, participants. Today, our speaker is from IIT Guwahati. Welcome to Dr. RameshBabu garu. Sir, can you hear me, sir?
Yeah, you're loud and clear.
Okay, sir. Is it clear, sir? Audience, is my voice is audible, clear and audible, sir?
For me, loud and clear.
Okay,
From
sir.
my side, clear.
Okay, sir. Okay, sir. Okay. Now, I'm going to give a brief introduction about the Dr. RameshBabu garu. Dr. RameshBabu garu Yatirajula has an extensive and diverse academic and professional background. His qualifications and experience. I'm going to read it out. A brief introduction about the Mr. Dr. RameshBabu garu. He done his BE in Electronics and Instrumentation Engineering from Andhra University in 2004 and MTech in Electronics and Communication Engineering VLSI System Design from JNT Kakinada in 2013. He has done his PhD in nanotechnology from IIT Guwahati in 2024 and he is AI and ML certified from Purdue University, USA in 2023. He has 6 years of experience in teaching for undergraduate students at engineering colleges, covering a wide range of subjects in electronics and communication engineering. He is having an industrial experience of 4 years, Dredging Corporation of India, a public sector undertaking contributing to the development and implementation of various technology solutions. He has done research projects and he is having 3 years of experience in working on high impact research projects, including nanotherapeutic, uh, nanotechnology based therapeutic and diagnostic systems. He has also done the project for Reserve Bank of India and government of and also for Government of India. He has done his research and development in nanoelectronics and related fields. His contribution towards the research and publications are publication research papers he included in 9 reputed journals, contributed a book chapter on topics related to his research, filed 2 patents with the Intellectual Property Rights Office in Calcutta. He has handled subjects like electromagnetic fields, theory, microprocessor and interfacing, digital communications, analog and digital electronics. Thank you, one and all. I'm going to share PPT, uh, and our sir is going to brief about the whatever he is going to give lecture on topic in his research area. Thank you very much.
Thank you so much, Suresh Garu, for your wonderful introduction. And thanks once again. And can we start?
Sure, sir.
Okay.
Participants, is the PPT is visible to everyone? Sir, is the PPT is visible, sir?
Yeah. For me, it is visible.
Okay, sir. Okay, sir.
Yeah. Now you can make it as a full screen.
Sure, sir.
So if it is full screen, then it will be good.
Okay, sir. Okay, sir.
Okay. Good evening to one and all. Myself, Dr. RameshBabu. Today's topic is design and development of high performance organic and perovskite light emitting diodes. And first of all, I would like to thanks to that Vignan Institute of Engineering, Women's in Andhra Pradesh, and then that funding agencies also. And then next, please. Next slide, please. Next slide, please.
Sir, is it okay, sir?
Right now, I'm only I can see the first slide only.
Okay.
It is not went to the second slide. You can keep in the that presentation mode or view or something.
Okay, sir. Sir, is it visible, sir? The first slide, second slide.
No, it is not moving.
Okay, sir. Sir, is it moving, sir?
No. It is coming also. That is not coming full way. It is coming like a supporting tool and that file edit tools that is coming.
Okay. Now, sir?
No. I can see only the first slide only.
Now, sir?
Still. Yeah, now I can see the second slide.
Okay, sir.
Okay, well, coming to the introduction of that light emitting diodes, now it is excellent. It is came the full screen also and everything fine. In 1880s, introduction of that incandescent bulb. As you know that in olden days that filament lamp was there. The incandescent bulb is producing a light by the passage of the electric current through a filament. And also it is those days it is in a Thomas Alva Edison. It is in a technical breakthrough. A new light comfort also came to the people's life, and the advantages are that good color rendering index, that the color rendering index is nothing but if it is in 100 it is equivalent to the sunlight. If it is more than 80 it is good for our human being retina, so that we are make the people will make that measure that value of the color rendering index. If it is more than 80 it will be good for the usage, and it is the cost also low, but no that toxic, the quantity of the toxic materials like other materials like tube light and fluorescent lamp. And here the main drawback is it is not that much energy efficient. Almost like 15 percentage will come and 85 percentage will go in the losses only, like temperature and other means. And it is also not useful for that lighting for the large surfaces areas. For example, if you want a nowadays you can see that LED TV and LCD TV are like very large screens, and also nowadays the so many solar cells are like there. The panels also large areas is coming like 1 meter by 1 meter and 2 meter by 2 meter and roll to roll technology and all. But if we are using this technology, we cannot go for the larger areas. That is the main disadvantages. Next slide, please. Well, coming to that second generation in 1937, that General Electric demonstrated with the first fluorescent lamp. The fluorescent lamp produces a light by the passage of an electric current through a vapor of mercury. You can see in that right hand side, that is the right nowadays that those lights also some still we are using. The luminescence, the advantage of this technology, the luminescence efficiency is several times better than that incandescent bulb. But while coming to the disadvantages, that lack of that quality, the CRI value, It contains that the culprit is that it contains the mercury and not useful for the lighting for larger areas. So considering these low efficiency of the incandescent bulb and the color quality of that fluorescent lamp, the color quality is nothing but the color should be equivalent to that sunlight. Otherwise, the human retina it cannot be able to detect, and also it is not good for that our human eye also. That's why we have to maintain the quality for a good quality of that light and light sources also. Otherwise, it will not they will not accept by the research community in globally. Internationally, we have to accept if we are making something or we are fabricating something, that device should be acceptable with the international research community. So that's why we have to take care of the remaining things also. So it is evident that there is potential for a substantial energy saving by the switching to a high energy efficient and larger areas also we can go. And in organic case, organic means a simple dimethyl layer is a polymer or monomer. And if you're going for a perovskite materials, that perovskites are these are hybrid. For example, methyl ammonium lead bromide. Here the methyl ammonium is the organic component, and lead iodide is the lead and iodine is the inorganic components also will be there. Later when we are going to there, we will discuss about why we are going for that, why that nowadays everybody going for the perovskite material, and why we are not using that previous technology. And then these are also eco-friendly. That means mechanical flexibility will be there. These are like flexible LEDs and flexible solar cells. We can make flexible thin film transistors and flexible memories also. Next slide, please. Yeah, thank you. While coming to the introduction to that solid state light emitting, in the past decades, a new class of light sources has emerged and referred to a solid state light emitting. Here we are having two different concepts. One is photoluminescence and second one is the ultroluminescence. In case of LED, these two are the very fundamental, and we need this characterization. And when we are excited the photons, you can see the left hand side, the luminescence will enhance, it will enhance also. And also here what will happen, like homo lumo, that is the conduction band, and homo is a valency band in case of organic material. When you are excited with the photon, that time it will go to the higher energy to the low energy to higher energy, and when it is coming back, what will happen? It will that is called delayed fluorescence will happen. Delayed fluorescence, what will happen? The excited state of electron and hole will combine, and it will give that is called exciton, and it will give the light energy. And it will, when it is coming, that light will come out, and the radiative recombination will happen. The coming to the right hand side, that electroluminescence, when you are applying a electrical source, that time the hole and electron will come and then recombine. By externally, we are giving the electrical bias voltage. With crocodile clipper, what are the means? We has to give that the plus and minus for a diode. That die means two. One is anode, another one cathode. We have to give the electrical bias. Next slide, please. Yeah, while coming to that types of solid state light emitting sources, inorganic and organics also there. These are, you can see that first one on top, white color inorganic light emitting diode. And these are all are that in our lab we fabricated the organic LEDs with different colors. Like all the colors you can see there, and green color and blue color and then white color, red color. These are all we fabricated in our Indian IIT Guwahati Organic Electronics Center for Organic Electronics Lab at the nano center. And also you can see that a simple table, inorganic and organic, and you just that in case of inorganic, the crystallinity is more, and these are very limited. Limited materials are available, like gallium arsenide, gallium phosphide, or gallium arsenide phosphide. If you are coming to that organic case, the plenty number of materials will available, and we can tune like we can tune, and we can easily, you can E is equal to C by lambda. you can make it as an SC is a constant. So the E is indirectly proportional to the lambda. The lambda is a wave number. So if you are varying that lambda, automatically the energy band that the bandwidth will change. Automatically the light will change. So, but in case of inorganic material, it is very difficult, and also very limited sources materials will be available. That is the reason why the people are going to the organic one. And also, in generally, these are the inorganics are the very point sources, and it is not useful for that larger areas. But in case of organic, we can go for the larger area, like 1 meter by 1 meter. We can go for it. And in case of inorganic, highly efficient and high lifetimes and mature technology. Here, the main reason is in inorganic. For example, if you're taking a silicon and sand to silicon, and then you can make it as a silicon dioxide. It will take high temperatures, 1200 degrees centigrade, and also the cost is required more and more. In case of organic, the cost also less, and also no need of that much temperature. Also, the processing temperatures maximum might it may be 180 or 200 or 240 maximum. That much temperature is also not required. That much sophisticated infrastructure also not required. And coming to that next one, here in case of organic, the new technology and holds the promising of that exhibiting a very good color rendering index. Color rendering index indicates the quality of the light. It is how much needed to the sunlight. Next slide, please. Next. 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 Yeah. You can see this that this is the sandwiched structure of that layer by layer. Anode will be there on top of that organic semiconductor layer and cathode. Here what we'll do, the sandwiching layer of the single layer, and then we are giving the electrical voltage outside, and automatically the electroluminescence will come from the anode. Here we will go for that in forward, then we can see how we can make it. Next slide, please. Next. Yeah, here you can see that what is happening here. You can see that left hand side, that anode, cathode, and also we have the emissive layer in between. And here you can see that a band diagram. The anode it is consisting of where a small circle is there. That is a hole. Imagine that is a hole, and that homo-lumo, that is the one is the conduction band and valency band respectively, and then cathode side, and then the dot red colored dot is indicating the electron. Next, please. Yeah, when you are giving a bias voltage, here what will happen? Bias voltage, the plus and minus, when you are giving that time, the whole also will come towards the emissive layer, and electron also will come in towards the emissive layer. When the hole and electron is recombining, the time what will happen? That is called exciton. Exciton means excited state of electron. When the hole and electron are recombining at the emissive layer, the light will come from that. That depends on the bandwidth or the what is the type of the material. The light color will come. And also you can see in the left hand side, the light will come through the anode side. One is the transparent side of that ITO, and the glass will be there. Light has to it come out from the device. So we will keep it as a one is a transparent side. Most probably cathode is like aluminum or silver, or we can use gold, but most probably in the silver, aluminum and silver is okay. That budget also within our limit. Next slide, please. Yeah, you can see here why the need of the multi-layer organic light emitting diodes. You can see that vertical way substrate. The substrate is like holding that particular our LED, and anode and cathode is there. In between the optional layers also there. MC layer already we discussed it. 3 layers are there. One is anode and cathode. In between MC layer, that is called EML. EML is nothing but emissive layer. L defines or indicates layer. And coming to the optional, here we can see hole injection, hole side, hole injection layer, hole transporting layer, and electron blocking layer. So why that multi-layers are required? You can see that after AEML also HBL is there, that is called hole blocking layer, and electron transporting layer, and then electron injection layer. Why these additional layers sometimes required? Because the hole mobility and electron mobility is not the same. When the electron is, if it is moving fast, or a hole is moving fast, that time what is required is we have to balancing that the hole injection or electron injection, so that recombination happens at the emissive layer only. We need not interested at the anode side or cathode side. That's why what we are doing is we are incorporating that additional layers or optional layers, so that the recombination will happen at the emissive layer only. For example, 100 electrons are coming from the cathode and 100 volts are coming from the anode. If you want 100% recombination, that 100 plus 100 it has to come. But our efficiencies will come around 80, 70 or 50, because that all are not going for the not contributing the radiative recombination, and also not giving the light outside. Some of the reasons might be like temperature losses and other losses will reduce this our uh, radiative recombination. Obviously, what will happen when the losses are there, the efficiency of that particular light emitting diode will decrease. So that is the reason why we want the multi-layer in our organic light emitting diode. Next slide, please. Yeah, if you're coming to that next one, the solution processing also there. The fabrication techniques, you can see the left hand side and right hand side respectively. Here, the solution processing of the polymers. The polymers are we can dissolve in that organic solvents will be available like chlorobenzene or chloroform. Chloroform compared to the chloroform, chlorobenzenes will give the very good films. Very good film give the very good devices, electrical devices like light emitting light LED, solar cell, and the organic transistor and organic memory and so on. Here the spin coating is a very simple technique, and we'll use that speed to control the thickness, and also we'll use the time also, so that the uniformity will maintain entire the substrate. And also Dr. blade technique is useful for the uh, it will go from the XYZ direction. So what will happen, it will like it is like a one, you can take a one bread on top of the jam, and it will spread very uniformly. This technique especially using in the larger area. For example, I need a 1 meter by 1 meter display, or 1 meter by 1 meter organic solar cell. That time we can choose this technique. This is the Dr. Blade technique. That is the second one, which is in the yellow color. And next one, that inkjet printing. Inkjet printing, it is matlab that ink that like a spray coating, that like your bike and our automobiles also for the car painting and like that, the substrate will be there. That inkjet printing will give that how much wanted to go, and what is the flow rate, and what type of injection is required, and what is the etching material. Like, yeah, depending on that we will go for it. And then third one is sorry, that fourth one. The fourth one is that the dip coating. Dip means we know that dip tea. Dip tea in one side we will cover with the masking tape, and one side only we required. One side we'll just dip like that with the spatula. So that what will happen? It will come nicely, and the total area will come dip coating. Nowadays, one of the we conducted one Indo-Japan conference. In that, even our most of the Japanese professors who are invented that so many good things, still they're using dip coating, because this is a very easy technique compared to that remaining all. But here the only the problem is viscosity of the material depends on the thickness also. We cannot control the thickness. That is only the main issue. Otherwise, it is like very easiest method to go for a biosensor or bio components. Those are very good. While coming to the evaporation, the right hand side you can see the evaporation of the small molecule. Small molecule means which is having a one unit only. The polymer means that n number of units will be there. I am also not a chemist. I am an electronics guy, and then we are working in the we are mainly focusing on the device engineering as well as the device physics inside what is happening, and we will fabricate the device, and then we will analyze the device, and then we'll get the those results will come, and how it is globally competitive, and then after globally competitive, and we will go for that characterizations like FESM, AFM, and then XRD, PL, EL, and TRPL, and to support that our electrical study. And coming to that here vacuum pump, you can see that evaporation of the small molecules. You can see here what will happen is here that bottom one is a crucible and heating coil will be there, and then that chamber is a fully high ultra vacuum will be there. On top of that, the substrate water will be there, and the piezoelectric crystals will be there. The holder means where we are keeping our sample, and then the crucible will be there. That will give the vacuum pump and also turbo pump. And with actually we needed around 10 power minus 6 millibar. Why? Because that the mean lifetime of the atom to be reduced. In that case, what will happen? It will go directly on the shutter only. It will not go here and there. And also, you can see that the piezoelectric crystals are there. It will give the direct thickness measurement. For example, I want a MC layer of 80 nanometer. It will give directly 80 nanometer only. We can close the shutter and we can do our that. This is called PVD, that physical vapor deposition, and we can get whatever the quantity is required. We can able to measure, and we can stop exactly at 80 nanometer. For example, I want 1 nanometer also, I can stop at 100 also, I can stop. According to the nanoscale range, I can able to stop it. And then, well, coming to the down one, the organic vapor phase deposition. Here also, we'll use that a simple organic argon or the nitrogen gas, and followed by the quartz tubes will be available. Here we will use that ceramic one. Ceramic board. Why? Because the reason is here the ceramic will keep the organic component. We'll give that heat with that. When it is coming to the sublimation temperature of the material, that time it will come and sublimate the material. It will give very nice films. It will give that according to the sublimation. Every material will have the sublimation temperature. According to the sublimation temperature, like water having the sublimation, also that boiling, also evaporation temperature. Like that, 100 is the for water. For every material in the universe having its own melting point as well as sublimation temperature. So we are using here a simple organic material will take, and then we will evaporate. For small molecules, it is a very good method compared to the spin coating. This is called how we evaporate a material to while going before going to the device. Next slide, please. The characterization. The characterization after making the device, what the internationally it should be acceptable by the research community. What are the main parameters required after fabricating the device? When we are doing a research, that should be acceptable by the internationally acceptancy should be there. So we have to maintain such a parameters, like you can see in that luminescence intensity is the measure of the wavelength. Also, it is called candela. As you know that everybody knows that what is the luminescence intensity, and the luminance. Luminance is nothing but is the brightness. That the brightness is per unit candela per meter square. That intensity with meter square. You can see that in the right hand side one sphere is there. Here you can see that the hemisphere, the light receiving surface area, and also 1 meter square, and solid angle and light. Yeah, it is a calibrated one. It is directly given by that CS 2000 spectrodiometer. The Konica company will provide, and the distance also they are calibrated. They will give, and simply like if the light will come, we can capture also exact value it will give. The small accuracy or resolution will change, but almost it will give the very finest values. Next slide, please. Yeah, coming to the CAE and color temperature. CAE means the Commission of Illumination of International Coordinates of the LED. You can see in this so many colors are there. On top green color is there, and bottom also blue color is there. And if we're coming towards that left hand side figure, I am discussing about the left hand side figure. If you're coming to that downward white, that red color is there, and in between that white color is there, like that. Why I'm showing this figure? That for example, if I'm having a 0.33 comma 0.33 x comma y coordinate, that is the white color. For example, if I'm adding 0.25 comma 0.73, that is a green color. If I'm getting a blue parameters or a red parameter or some parameter, it should be acceptable in international community. Why it is required? If you're making a device, why other people or other industries should accept our otherwise other research community, why they has to accept it? That's why a common platform for globally, that if you are making a emissive material or emissive component, that time what is required is here that mainly the CIE coordinate is the main important. That's why we are measuring it, and it will give by the that device itself. No need to worry, and that CS 2000 will give. If you are getting a good light, it will come automatically. It is one of the measurable parameter to quantify that quality of the device. And coming to the cool colors, the temperature at which a black body would emit the radiation of the same color as given by the object. And here, the temperatures, the over the 5000 Kelvin are called the cool colors. And warm colors are in between 2700 to 3000 Kelvin are called the warm colors. So here, if it is more than 5000 Kelvin, those are good for the cool colors. Next slide, please. And if you're coming to the next interesting one, earlier also in one I discussed this is CRI. You can see right now that color rendering index. It is called CRI. A color rendering index is a quantitative measure of the ability of a light source to reveal the colors of the various objects faithfully in comparison with the ideal or the natural sunlight. The natural sunlight means that is natural light source, that is the sun only. For the human being, if you are wanted to do some technology in perspective of the semiconductor technology or any technology, that should be acceptable, that should be purchased by the end user. End user is the customer. So that should be needed to the sunlight, then it is good. Now you can see that one small partition is there in the bottom figure. The same colors only. If the CRI is greater than 80 or less than 80, how it is resembles or how it is, you can see. The green color, you can see left hand side, the green color apple, and then orange also, you can see orange color, and apple also the same color. And if you're seeing the right hand side, you see when the quality of the light is not good, then automatically the color is not, that orange is become the dark, and also apple, the green apple also you can see that green apple also it is not good, and also apple also it is not good. You can see that the salad also in the extreme right hand side, and top the CRI is less than 70, the grapes and other, I can see the fruits, how it is looking. And if the CRI value is more than 80, how you can see that quality, that the same material, if that color index is not good, then it will not good for that. And also some of the people in that shopping malls and all, they will how they clever, because they will keep this type of filtering technologies, and they will make it very beautiful. And after shopping and after coming to the home, we will go for a shop, and then what we are purchased and what we are right now seeing, That also this they will play with this ARI index only. Next slide, please. Next one, please. Yeah, next coming to the fabrication, our OLED fabrication technique in organic light emitting diode fabrication technique. Coming to the first point on top left side, this is called glass on top of ITO. Glass is the bottom one. The next one is ITO. ITO is nothing but that is an anode, indium doped tin oxide. That we will using as an glass is for the to escape that light. So that's why we're raising a glass. And I2O is a very transparent electrode. That is a conductive material and also it is a transparent also. That's why we have selected this ITO. ITO is nothing but the indium tin oxide. Well, coming to the second figure, we will use that simple scotch tape and we'll make that, you can see that 4 plus 4 are there. And here 4 plus 4, 8 LEDs will come at a time for a single substrate. If you are keeping for 10 at a time, 10 into 8, 8 LEDs we can fabricate at a time. So the scotch tape will be there. On top of that, zinc dust and concentrated HCl will be there. That is available in the market only. You can etch that particular portions where it is required. We will expose it to that. We will not expose. When where we are wanted to etch that particular portions will etch. You can see nicely. One is that common cathode one, and the anodes are will be available. And here we can make in one single substrate we can make 8 LEDs at a time. In like that, if you're keeping a 10 substrate and 10 into 8, 80 devices will come at a time. 80 devices means we can get 80 number of that characterizations, 80 number of ELs, so 80 number of voltage study. And you can do that how that light efficiency versus that other parameters. So that's why we are keeping as it a single substrate we are making like that. And also we can go for the next layer, that is P dot PSS. The P dot PSS is a synthetic metal, and also it is a very good for the whole injection. That's why we are using as a whole injection come transport layer at the anode side. And coming to the fifth one, the spin coating layer with the MCU layer. Will spin coating, and then it will uniformly it is spread. And then now you can see the color also. The previously one color is there, now the color is changed. And then we will go for that aluminum deposition as we discussed earlier. That is thermal deposition or PVD. We discussed that ultra high vacuum will be there, and then we'll keep our substrates and holder at top, and then piezoelectric will be there, and bottom will keep that aluminum or whatever required like aluminum or silver or gold. We can able to deposit. At the deposition also we can stop at exactly if you want at 100 nanometer, we can stop at 100 nanometer only. Next slide, please. Next one. Yeah. Well, coming to the perovskite materials. Here, what will happen is why that till now we have discussed about that how we have to fabricate an organic light emitting diode that is called OLED. Why are going for the perovskite materials? Because the perovskite materials are which is having very finest way and crystallinity also very good. When the crystal is good, that automatically the mobilities will be good. And also these are we can the color tunability is excellent. Color tunability means, for example, the methyl ammonium lead bromide, if you're taking if I'm taking a bromine, it will come green color. If I'm taking a chlorine, it will come blue color. If I'm taking a iodine, it will come the red color. If I'm mixing all these three, then it will come that is called mixed halide. I will get a white light also. If you are getting a white light with the simple organic or any other substrate, other sources like inorganic is very difficult. But in case of perovskite, the cost also less, and also we can do the spin coating and simple technique we can use, and also processing temperature not required like silicon technology. It will require around 1200 degrees centigrade and all. But here only processing temperatures are 140, 180 below 200 degrees only. And also the main thing is the tunability. And also it can use it for the flexibility also. We can make a nice flexible LEDs and also flexible solar cells. In case of if you're going for the northern region or northern pole or nearer to that, there is a very the tents are for the soldiers and all the tents are available. The tents are not in the shape of the what is exactly circular or triangular or like that. So it is not that the shape is matters there. So if it is flexibility is there according to the shape, we can paste at any area. So when the sun will come, we'll take that absorb that the photons, and again it will give the voltage. That voltage again give the light energy. When you are giving a voltage to that time, they now the electrical energy converting into that light source. So that is the why we are going for the perovskite material. Here you can see that a single hole HTL means hole transporting layer. Best high efficient perovskite LEDs. Here FTO. This is our lab work. We published recently, and FTO, and that is called fluorinated tin oxide like ITO only, simple. And bottom one is the glass, and the whole transporting layer is P dot PSS, and we compared with the three different parameters. And comparison study we did that how the modulation of the carrier injection is happening towards the whole side. And also on top of that perovskite material, simply we are mixing that methyl ammonium bromide and lead bromide, and we make that precursor inside the inert gas in the globe box. And then we are making with the spin coating, we are keeping a nice 90 nanometer thin film. On top of that TPBA, it is called as a TPBA. It is called as a electron transporting layer, ETL, and followed by LIF aluminum. LIF is nothing but it is in a cathode interfacial layer. We are fabricating with 1 nanometer. And what is the advantage of this LIF is it is used as a cathode interfacial layer, which is allowing that tunneling effect inside the device. And on top of the final layer is aluminum. So the anode cathode will be there. We are giving a simple forward bias. And here these are the four molecules you can see P dot PSS, NPD, PVK, TCTA. We are in place of we what we did, we kept that P dot P all the layers we changed, and how that hole and electron are going inside the device. And you can see that current in the third figure in the bottom one, bottom first one. So the current density versus voltage and luminescence versus voltage, the luminescence versus current density, that current efficiency versus these are all our electrical parameters. It is following that diode exponentially also, and also it is giving that good the luminescence brightness is also we got almost more than 24,000 candela, and we got that very good that luminescence efficiency and external quantum efficiency. The luminescence efficiency is nothing but the candela per ampere, the output by input. Here input we are giving that in the electrical way that 1 ampere, how much candela we are getting. That is called the luminescence efficiency. That is called capital L dot capital E. In the unit of the luminescence efficiency is candela per ampere. If we are getting this parameter is good, then our device is very good. And then you can see that EL intensity in the bottom middle one, the EL intensity versus the voltage. You can see the very nice the comparison of that EL spectra. That green color is the NPD based device, that is the champion device, and the way compared to, you can see the PVK, that blue color, and P dot is the black color, red color TCTA. In this study, what we observed is with the EL intensity, electroluminescence intensity study, we got that 533 nanometer, the good green lambda peak, the wavelength peak, and then we got that highest champion device is the 10PD based device. That is the you can inside you can see the green light also. Then if you're coming to the B figure B, that is the CI coordinate. It is coming in the good green one. So what is happening here? It is coming like it is coming like you can see that different parameters are there, and the CAE coordinates you can able to see P dot PSS, PVK, NPD, and TCTA respectively. And then, while coming to that, a single HTL based. Next slide, please. That CAE coordinates done. Yeah. If we're coming to the next studies, here FESM, it is called the top one is the FESM, field emission spectroscopy. Basically, what it will give, how that the grain size and grain boundary, and then how that morphology look like. After, if you are using the NPD as a bottom layer, we got a very good crystalline in nature, and also less pinholes are there, less traps are there. So that's why the C is the champion one. We got that, I can see compared to that others, A, B, and D, the C is the good morphology we got. And also we went for the XRD study, and XRD, it will give that how crystallinity it is. If the bandwidth is very low, then the crystallinity is good. And 100 and 200 or 210, it will give that exactly whether the perovskite layer formed or not, and also how good the that crystallinity. How if it is a very narrow, then automatically the crystallinity will be good. And then what we observed in this study, the NPD based device, we got the less one bandwidth, and also full width top maximum also very good for the NPD based device. This is the XRD study. And then we went for the photoluminescence study, third figure, on top, third figure, the PL intensity versus wavelength. And then here you can see that red color and the other parameters, the green one is predominated compared to the others. It is a simple photon, like initially what I discussed, when the photons will go, and then it will emit, it will again, it will collected from the receiver end. And then that in this study, the maximum also, it also came almost like 535 nanometer in the range. Both are well matching that EL and then our PL study also. So compared to that fourth figure on top, this is called TRPL. TRPL means time resolved photoluminescence. Here what will happen? One component is exponential component will the trap studies, and second will give that radiative recombination. The both we can get into that, and how much lifetime, which one is giving the higher carrier lifetime, that is the good for LED. If the carrier lifetime is less, that is good for LED solar cell. So here you can see that carrier lifetime is much more dominant in case of NPD based device compared to the PVK and TCT and P.PSS. And then here in this study, what we observed is here that the carrier lifetime is very good in the NPD based perovskite LED. And we will coming to the stability study. In the bottom one, left bottom. In the left bottom, the luminescence in percentage versus time, we studied up to 300 minutes. And here, you are getting a maximum for that green color one, that is NPD based device. NPD based in the perovskite device, what is happening? The remaining guys are not retaining, but our NPD based device got the retaining up to 79%. The degradation is happening. Most probably that the degradation may be the cause of that ion the ion migration is happening inside device and the thin film. So that might be might be the possible reason to it is not retaining the and light. So well, coming to that summary, you can see that device parameter and the turn on voltage, luminescence, and then external quantum efficiency percentage, current efficiency in candela per ampere. Here compared to that P.PSS and the other rest of the three, the PVK, the second also a comparison, that NPD one, it got almost 4.7 the less turn on voltage, and also the brightness or luminescence we got around 24,343 candela per ampere. Sorry, candela per meter square. That luminescence will come in the unit area. And the external quantum efficiency 6.79 and the current efficiency 16.2. It is one of the best result so far. And also we are published this paper. And then, well, coming to that next objective, this is a dual HTL. Please go to the next slide, please. Yeah, here in this next objective, we can get that dual HTL based high efficient perovskite LED. Here, what we did is how that second layer, how the dual means two layers, two all transporting layers will be there. How the second layer is reducing the turn-on voltage. When the turn-on voltage is reducing, like in VLSI, what will happen? The three parameters will be there. One is packing density, and second one is the speed, and third one is our power consumption of the total entire circuit. In that, what is happening when you are going for a turn-on voltage? That minimum, the turn-on voltage is nothing but it is a minimum voltage required to operate that particular device. Or when when the light will come, when it is exponentially starting, that in the diode curve that is called turn-on voltage, as you know. And here, in this case, what we are doing by incorporating a second order transporting layer, we observed that after keeping the second order transporting layer, that turn-on voltage is reduced a very good manner. Like 4.72, it is almost came down to 3.8. That is then a very good achievement. So that if a single component we are getting in a R&D level, that much, if I can do that very good in future. Then here what we did, we applied that P.PS is a constant layer. Sorry. And here what will happen? P.PSS will be there. Here P.PSS is the simple one layer. But here the energy is not sufficient to go to the whole will come from the FTO2, then minus 5.1, minus 5.4. You can see the second figure, B figure, in the bottom one. B figure, bottom one. And minus 5.4 and 5.6, the whole will come in that way. You can see in the top side that aluminum is 4.2. When you are adding that cathode interfacial of LIF, it is coming to that minus 3. And then TPB at 2.8 and then 3.6. The electron will come from the perovskite top and hole will come from the 5.9 side. So the hole and electron will recombine and then it will give the radiatory combination. And also you can see the electrical characterization, the current density versus voltage. And also you can see the luminescence versus voltage. And then luminescence current density. Here we got the very good luminescence 19.4 candela per ampere compared to the previous work. And also external quantum efficiency 8.05 and turn-on voltage we got 3.8. It is also one of the good achievement. And the EL intensity versus wavelength also we had taken like last time, the EL spectra. And we got the very good for that the dual layer of the P.PSS followed by NPD layer. And PL also we got a very good manner in the photoluminescence study. These are all our photophysical studies. And EL is the electroluminescence we are taken from the, when we are giving the bias voltage, we are observed from the light source. And also you can see that in the bottom third figure, the P.PSS, FESM, and P.PS NPD and P.PS PVK. In case of NPD, what is happening? Yes, spin holes are there, and also less traps are there. The grains are very smaller. When this the crystal kinematics is happening, that time what will happen is the crystal size is reducing. What we observed is we are getting that in nanoscale. Nanoscale means around 18 nanometer grain. This is very helping in that LED. For example, if you are getting a 200 nanometer and 500 or micron range, that will be good for the solar cell. But here, the smaller gains are good for the LED. In that case, in case of solar cell, what will happen is, in solar cell, we require that higher grains required for the absorption. And then you can see that CAE coordinates also. The CAE coordinates, you can see that X, Y, and also it is giving a very good the Commission of Elimination of International Coordinates, we got the very good colors and X, Y coordinates. And this also published. And then please, next slide, please. Next, next, next. Yeah. Here you can see this is our group leader, our Professor Parameshwar Krishna Iyer, and he is a multi diversity. He will be there. He is working in the so many fields like organic solar cells, organic light emitting diodes, and organic thin film transistors, organic memories, and also he is working with that Alzheimer's diseases, and also we are working with that biosensors for that multiple biomarkers like BP and then other sugar and other techniques also. And also here what we'll do, the chemist will do the chemistry part, and as engineering students and the other background like biomedical engineering and other students will do that fabrication of the devices. Here you can see that the IITG, that organic thin film transistor and LED, you can see the top one is OLED, and then other is simple with the writing. Then we'll show that other LEDs also. And here you can see the organic field effect transistors. It's like a mask will be there. According to that a mask it will come. Where is that source, drain, and then where is the gate, and then what are the layers are there. These are the flexible. You can see also when we are holding with that with the fingers, it is coming like a blend. It is like a bending. That is that is the beauty of that organic electronics. We can do that mechanical flexibility is very good. So what will happen? That flexibility is too good. And at the bottom one is organic photovoltaic, that is solar cell. On that flexible solar substrate, that is the main reason why the people are looking towards the organic and perovskite material based LEDs. The flexibility and the color tunability is the good one. So next slide, please. Next one, please. Yeah, we can see these are that organic electronics laboratory. These are the INEP facilities also. INEP is nothing but Indian Nano Electronic User Program. It is funded by that Government of India MIT, Ministry of Electronics and Information Technology. So anybody can come to the IIT Guwahati to Nano Center, and then you can come familiarization followed by like 2 or 3 months, and then followed by 6 months. We can do that that project will be there. And here what we'll do, we'll fabricate the devices. And also for you, if you're coming to that IIT Guwahati INEP facility, they will assign one faculty mentor as well as one dedicated one scholar also. So that if somebody wanted to fabricate some devices, there's some transistors, some supercapacitor, otherwise light emitting diodes or sensors, and then in some microfluidics based on biosensors. And so the IIT Guwahati is one of the very finest place, and you can come and you can go to the website also. So many facilities are there. You can come and you can do your research work, experimental work, and you can, and also they will help the writing in that. The scholars will help in that writing in the paper and patent also. Not only training, and also they will help to how to write a paper and how to write a patent also. And here you can see the globe box is there and the extreme top side. The globe box is nothing but globes is will available inside the net atmosphere available. Will maintain that oxygen level is zero. H2O is like very minute one. That's why it is globes are there. That's why it is called globe box. If the external atmosphere parameters will not affect our organic what we are doing. That is the main reason why we are keeping inside the inert atmosphere. And also we need that oxygen sensor will give almost zero. There is no oxide inside. When the oxygen is not there, the oxide of that aluminum will not happen. Otherwise, if you are keeping in an open area, the aluminum will very fast. It will go for that aluminum oxide. Then it will be like a insulating material. And also sometimes it will peel off also. It will react with the oxygen. That's why we are keeping inside that one. All the layers also will keep inside. Even the perovskites also, one of the drawback also, that will, if you're keeping outside, it will degrade very fast. But it required some encapsulation techniques also. If you're keeping the encapsulation and then some resins and robotic or some technique, then it will be excellent. Then you can go to that second one. In the second figure, you can see the surface profilometer. Here, this is the instrument to measure the thickness of the thin film. For example, if you're after fabricating that, after the spin coating the P.S.S, how much thickness is there, it will give. Then we'll go for the next level. So that's why it is an instrument used for the thickness to know the thickness of the thin film. Then we can see that already we discussed that how to do that remaining layers in the previous slides, and you know that how to make a MSU layer, and aluminum will do with that. And coming to the that micro probe station, this is provided by the lakeshore, and it is simply having a source, drain, and gate electrode will be there. One is for the photo emission. That is the fiber optic cable will be there. 4R will be there, and SVS, that is called semiconductor characterization system. I will integrated with that. Then automatically we can measure diode, and then we can measure that four terminal transistors, and then we can measure the memory properties. We can measure the biosensor also. So here the very good resolution that microscopy also will available, and will keep the chamber inside, and then we'll make the contacts also with the tungsten based our tip moment. So it will be give that very good result analysis, and also it will not allowing for that any hysteresis also, any contact errors also, contact with that our source or drain, the metal part, metal element, and the metal electrode. Then we can see the solar cell here. Solar cell, what we'll do is, after fabricating the device, we will take out the device and we'll check that our how much PC, that power consumption efficiency is coming. That is the main reason why we are fabricating, and we got almost 25 percentage. Globally, they got almost around 30, and in our lab we got 25. Still, we have to improve in it. And then you can see that in the middle one, that is the middle first one, that is the UV ozone treatment and illumination. Normally, after before going to the spin coating, we required a ozonation technique. That means that it will give the hydrophilicity. Hydrophilicity means it will spread very nicely. Hydrophobic means it should be like a that surface tension will be very high. That's why if you want a spreading nature is required, then hydrophilicity. Hydrophilicity, what will the property? It will give that where our solvent, our material is there with solvent, that will spread very uniformly. That's why we are using this technique. That is UV ozonation and deozoonation, and followed by electrochemistry also there. If you want to know that what is the homo-lumo, and how that with the frequency response with that, if you want the impedance versus frequency, that R will come. That R is that what is the how the nyquist spot is coming, and which nyquist is good for our LED, and how much impedance is needed, and which one is high and which one is low. For comparison also we are using this. And then we are using that IQE and EQE, external quantum efficiency system also. And I can see that LED tester also. LED, it will give that that EQE from this LED tester only. And then you can see the spin coater. We are using inside that globe box. Inside the globe box, for example, if you are spin coating inside, what will happen? It will not degrade that much easily. And then one channel will be there. We will transfer to that globe box to that. First, initially we do the spin coating inside, and then we'll transfer, and then we'll do that next layers, MCU layers, and then followed by metal layer. And then this is the simple furnace, that is the with vacuum furnace, and thermal deposition chamber also you can see. Here we'll keep that bottom, we'll keep that four are coming in the projections. That those are that where we'll keep our crucible, and then we will give that electrical voltage, and it will sublimate. That is called the thermal deposition chamber. So the thermal deposition, what will happen? Here it will is increasing. And then, while coming to the organic electronics laboratory, here what will happen is, here we can see the series combination of the four organic bulk heterojunctions are there, and we are kept a series combination. We got around 1.72 with the simple. Please go to the next slide, please. Next slide, next one, please. Yeah, this you can see here now, organic electronics laboratory. Here you can, the top one, you can see that left hand side, the series combination of the four organic bulk heterojunction solar cells are there. With a simple table lamp on top, on below you can see the box one. We with the simple technique, like with aluminum foil, we that aluminum foil for the food packing and all we will use. That aluminum foil we taken, and then we seriously combined that. That cumulative came 1.72. 1.72 is not that much easy for outside. The simple table lamp. That 4.7, if you are keeping a multiplier with some 10 or something, then it will come very good manner to we can drive so many components in outside. And you can see also the single bulk heterojunction, and then combination, and then flexibility also you can see that purple color fingers you can see the flexibility also we can see the figure. And then this is the combination also you can see in the, these are all are these are studied in our lab itself. And then you can see that 3 plus 3 6 number of how we are kept, and then how it is very flexible also. That projections also we did with that simple aluminum foil only. That one anode and cathode, and how to collect that electrons, and then how to preserve as an voltage. In solar cell, what will happen is exactly opposite way. That when we are giving the photo energy, it will store the voltage. Next slide, please. Next one, please. Yeah, here you can see, here this is called organic thin film transistors. Here you can see that 1 centimeter by 0.5 centimeter, how many are kept? Like one source drain, the middle one is gate, source drain, source drain, source drain. You can see almost 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 10, 10. These are 10 offsets are there inside. And then that projection you give the gate, the top one, the gate, will keep the gate, and these two are the source and drain, and 40 micron channel will be there in between. In the A figure, if we'll come into the B figure, we'll use the mask. This is the another one, another type of transistor. Here also source drain will be there. This also 3.5 centimeter by 3 centimeter only, and also flexible also. We are using a PET. PET for that flexibility that substrate. And then it is like our OHP sheet only, but it is one side is conducting, other side will not conduct. We have to do that etching of that material, so that will make our anode on top of a OHP sheet also. And then you can see that how that gate you can see gate is there, and aluminum is that our bottom gate, and aluminum oxide is the first dielectric. And the polymer dielectric also we are using like PVA, PMMA, polystyrene, PS, and PVP. And then why we are using that two dielectric? Because to reduce the threshold voltage. And then we can go for that NDI and CY2, that is called the organic semiconductor for that our main conductive layer, semiconductor layer. That is the common, that is a polymer which is having that p type or n type, that is dependent on the polymer itself. And then we will make the nice source and drain on top of that. So we'll give that source drain, and we'll take the drain characteristics as well as the transfer characteristics, and then it will give that very good transistor properties also. So this is the NDICY2, that is the polymer name and based OFET. Next slide, please. Next. Yeah. Here you can see that these are all our lithium green dyes we have fabricated in our lab. You can see that blue color, and then green color, and yellowish color, and then red color. And then you can see also IIT patterned also. IIT in our lab only we have patterned that, we wrote that IIT. And then followed by OLED flexible also we made with that simple that PET substrate, and with the OHP sheet itself. And these are the some of the outcomes from our lab. And this is simple. We varied that different colors and different combinations, different combination of that material, and then different combination of our mixed halides. We got that so many colors also. That is the beauty of the organic electronics. The main thing is we can tune nicely. In case of inorganic, we cannot tune this much easily. Next slide, please. Yeah. Well, coming to the some of the polymer LEDs fabricated in our lab as I showed, and also we can see that how we are giving the bias voltage. Bias voltage with that you can see in the crocodile clip, and one side anode and one side is a common cathode and common anode, and how we are illuminating that. And the PFO based also we used. And our sincere thanks to the Science and Department of Science and Technology for their financial support. And my sincere thanks to that Vignan Institute, Women College, for the giving that opportunity to in front of you I can make the presentation. And also that funding agencies who are doing that ATAL faculty development program. And then my sincere thanks to that for your kind attention for all the participants. And thank you so much. I'm happy to take the questions. I'm from my side it is completed. I am very happy to take questions. If any questions, please kindly let me know. Thank you one and all.
Sir, so let participant ask questions to you, sir.
Okay, please read once. Accordingly, I can answer.
Dear participants, you can unmute your mics and you can ask if you have any doubts to RameshBabu. Please.
If somebody hesitating, they can keep in chat box also, so that our Dr. our Suresh sir will share, and accordingly I will answer also. If somebody is shy or something, you can post in the chat box itself.
Sir, good evening, sir. I am Dr. Selvin from DMI College of Engineering, Chennai. Actually,
okay, sir.
Presentation is very nice, sir. We also we never expect so to fabricate the LED. These are the things are behind this. So we have elaborate notes to us. But I have a small doubt, sir.
Please, sir. Please go ahead.
Sir, if it possible to visit your lab, sir.
Yeah. Sure. That's why I showed that INEP facility. The INEP is nothing but it is possible itself. Why I'm saying you can write a mail to that Professor Iyer sir, Professor Parmeshwar Iyer sir, or Professor Dipankar Bandapaj sir. You go to that Nano Center website, IIT Guwahati.
Yes, sir. Before that,
list will be there.
Because we are from Chennai. Before leaving there, we got to send any formal letter to.
Yeah. That's why what I'm saying is first you have to write a mail, then so that I can also help, and also that facility itself that is for free of cost. That if you are coming there, then only we have to take. If you are working somewhere, you have to take that the permission for 10 days, and you can come there. You can come to IIT Guwahati, and then you can use the facilities also.
Is there any limitation, sir? This number of students?
Limitation will be there. For example, if for one batch we are going for 30 members for the three month project and 6 month project.
Yeah, sir. Which mail ID we have to communicate, sir?
The mail ID you can right now in the Nano Center web page, INUP ITI is there, like ISC Bangalore and then IIT Bombay. And here we are third place right now. We are having a very sophisticated labs. You can check in that CFN, that is called Center for Nanotechnology. And you go to the internet web and then just type that IIT Guwahati Nanotechnology, and you can see that facilities and then how to approach that INUP also. All our direct links are there. You can write there and you can able to see there.
Yeah,
INUP ITI is, you can write just IIT Guwahati INUP.
Okay. Thank you. Got it, sir. Got it. Thank you.
INUP. Just type and you will get all the information from there.
Okay, got it, sir. Got it.
Any questions, please? Any other questions? If somebody having other questions, you can write a mail also y.ramesh@iitz.ac.in. Otherwise, you can check in that our web page also. I can able to help you.
Sir, just share your mail ID and WhatsApp.
y.ramesh. Sir, please write y small y for Anki.
Sir, is it possible you can type it on the chat box, sir?
Actually, right now I am presenting, but here that we are having some problem is happening here. What is happening here that Wi-Fi issue is there. That's why you please write, sir.
So
y.ramesh@iitg.ac.in. y.ramesh. Ramesh.
I put it in chat box.
Okay. iitg.ac.in.
Yes, sir.
iitg.ac.in. IN.
Okay, thank you, sir. Thank you.
Okay, it's my pleasure, sir.
Okay.
Dear participants, if you have any doubts, you can ask to Sir Ramesh Garu.
If somebody having some shy or something, you can chat box also. Later on, I will communicate with Dr. Suresh Garu, and then we'll follow up it. Okay, thank you. If no doubts, and I am very happy. Okay. And thank you so much. Thanks a lot for your kind attention.
Thank you.
And the next also that.
Sir, one small doubt, sir.
One more. Please go ahead.
Sir, how to identify the metal? How to identify the metal for LED fabrication, sir? Which metal is comfortable to us, sir? I think silicon.
Material. You're saying material.
Yes, sir.
With simple metal, it is not possible. With simple metal, not possible, but with material needed. For material, like for example, in commercial angle, that ALQ3, this is the material which is having the band gap of, for example, 3 to 3.6 is good for LED.
Okay.
We have to select how the band gap is there. The first criteria is like we have to check the band gap of the material and how the homolumo, like valency band and conduction band is there, and what are the HTLs that we are using. Accordingly, we have to select the MCU layer. First band gap, second one is the energy for injection of the holes and for injection of the electrons. Then only the proper recombination will happen at the center only. Otherwise, what will happen is it will recombination will happen at the extreme left hand side or right hand side. That means cathode or anode. That is not in that much good for that good efficiency. The recombination, we are interested at the emissive layer only. That's why we have to select the materials such a way that energy also should be matched. Second one, the homo-lumo also, and then that after thin film, the quality of the film should be good. That quality means the morphology. If you're taking a atomic force microscopy, the topology, that should be good. that is the main motive.
Sir, how it is calculated, sir?
The calculation is like simple. We have to take that UV visual spectra. One study is there.
Okay.
UV will get the we can get the band gap directly. Otherwise, we will have the DFT calculation. DFT means that is the Fourier transform. That is a simulation. Otherwise, you can take any band gap also. Otherwise, so many materials are available right now in the literature itself. You can pick a one material, one commercial material, and you can change the other layers.
Okay, sir. Okay. Thank you, sir. Thank you.
Yeah. Okay, thank you so much, one and all. Thank you for Vignan Institute and also all the funding agencies and all the participants for your kind attention. Thank you so much.
Thank you very much, sir. Thank you for your.
Then the next talk will be on the solar cell. He is from Dr. Suresh from IIT Guwahati, and he's completed his the PhD from IIT Hyderabad and MTech from the IIT Kanpur. He will give the talk on the solar cells. Let me confirm also. We'll please stay there, and then he will share that slides. Okay. From my side, I am signing off. Thank you so much.
Thank you, sir. Thank you very much, sir. Thank you for your valuable talk on LEDs, sir. Thank you very much, sir.
Thank you. Thanks a lot.
Hello, sir.
Sir, good evening, sir.
Sir, I am Dr. Suresh.
Sir, welcome,
yeah.
sir. Welcome to ATAL.
Yeah, I have shared my slides with you. So,
okay,
are you able to present or should I present it?
Sir, sir, I'm going to give a brief about you, sir, for participants.
Yeah.
Later,
Okay,
we can
go
share
ahead.
your PPT, sir.
Yeah.
Very nice. Good evening. Now the speaker is Dr. Madhuri Suresh Garu. He belongs to Department of Electronics and Electrical Engineering, Center of Nanotechnology, IIT Guwahati, Assam. Now he is doing postdoctoral fellow at Electronics and Electrical Engineering, Indian Institute of Technology, Guwahati, and he is a advisory professor, Roy P. Paley, Department of Electronics and Electrical Engineering, Center for Nanotechnology, Indian Institute of Technology, Guwahati. Now, his research work is simulation, fabrication, and integration of organic photovoltaic cells and green hydrogen production for photovoltaic cells. He has done his doctorate in 2023 in Indian Institute of Technology, Hyderabad. He presented thesis, design, fabrication, integration of thermally evaporated bulk heterojunction organic photovoltaic cells for IoT applications. His research focus on mainly on extensively worked on bulk heterojunction organic photovoltaics with a strong focus on microstructure design using vapor processing techniques. He did his master's technology in photonics, science and engineering, Indian Institute of Technology, Kanpur. Now today he is going to give a brief session uh, in which he is very expertise. Thank you very much, sir. Sir, now you can continue. Sir.
Yeah, thank you very much, sir, for your introduction. I am privileged and honored for this invited talk. So I am very thankful to you. So, sir, can you present my slide so that I can?
Okay, sir. Sure.
Yeah.
Sir, can you share in WhatsApp, sir, so that I can open it directly, and from there itself I will.
Yeah, I already forwarded.
Let me see, sir. Let me see.
Yeah.
Sir, okay. Got it, sir.
Yeah.
It will take a few minutes, sir. Just.
Sir, I'm unable to see presentation.
Just a minute. Okay, sir. I'm sharing right now.
Yeah. Okay.
Sir, can you able to see the presentation, sir? Is it visible, sir?
You can put it in slide view mode.
Sure. Sir, okay, sir.
Yeah. But slide view mode is not coming here.
Not it, sir. Okay.
Yeah.
So is the
Slideshow is not coming.
Okay. Sir.
Otherwise, should I do it? Slide view.
Now is it
From
okay, sir?
beginning. From beginning.
Is it okay, sir?
But unable to see that one. Okay. Anyway, so sir, if if it is possible, I can do it from my side.
Okay, sir.
Screen sharing.
Okay, sir.
Yeah.
Sir,
Host
now
disabled
yes,
participant.
yes, sir. I make you host, sir. Now you are the host, sir.
Yeah. Okay. So, yeah. So is it visible, sir?
Sir,
Hello.
it is visible, sir.
Yeah. So now I'll continue. Okay. So thank you very much once again for inviting me to this.
Welcome, sir. Thank you.
ATAL FDP 2024 talk. So today the uh, title of my presentation is Next Generation Photovoltaic Cells for today's contemporary applications. So the outline of my presentation is introduction, classification of photovoltaic cells, and motivation of organic photovoltaic cells, and the advancement of different structures of OPV cells, and their fabrication method, characterizations of these OPV cells. And then I'll be going to conclude about this next generation photovoltaic cells. So first, let me introduce the solar cells. So we all know every activity requires energy. Electricity is the most useful form of energy, and if you see outside, the sun solar energy is abundantly available. And if we are able to convert the sun solar energy into electrical energy, that will be very useful energy. So therefore, there is a device called a solar cell device which converts sun solar intensity into electrical energy. So this works on the principle of photovoltaic effect. So photovoltaic effect is nothing but when light shines on the material, it generates photovoltage or current. So this is uh, I mean depicted in this schematic diagram. So there is a photoactive layer between two electrodes, anode and cathode. As soon as light shines on the material, it generates electron hole pair, and this will be dissociated and reached to the respective electrodes. And this is the ideal solar cell equivalent model. So I mean, solar cell is nothing but a diode. So diode in parallel with current source. This is the ideal solar cell equivalent model. So coming to the classification of solar cell. So from way back from the beginning, the solar cells are divided into three generation solar cells. They are first generation, second generation, third generation. First generation solar cells are nothing but crystalline silicon solar cells. Like whatever the present solar cells which are available in the market, these are crystalline silicon solar cells. I mean, if you see in offices or some homes, they are installed solar cells. Those are based on crystalline solar cells. So, and coming to the power conversion efficiency, they are from 18 to 24% highest power conversion efficiency, and these are highly efficient and highly stable. So, coming to the second generation solar cells, these are amorphous silicon, cadmium telluride, cadmium, indium, gallium sulfide, CIGS solar cells, and their power conversion efficiencies are ranging from 12 to 20%. And the advantage of these second generation solar cells are they are low cost. And coming to the third generation solar cells, these are organic solar cells, dye-sensitized solar cells, perovskite solar cells, and their power conversion efficiencies are ranging from 5 to 24%. And the main advantage of uh, the third generation solar cells in comparison with the first generation, they are low cost, flexible, and lightweight. So because of these reasons, people are working in third generation solar cells. And now I am going to talk about the particularly organic solar cells. So why organic solar cells? Organic solar cells have uh, distinctive advantages, and they have potential applications also in comparison with the first generation solar cells, because first generation solar cells are very costly. That's why uh, many of the people cannot able to afford, and they are not able to install in their homes. So here these are flexible, transparent, lightweight, large area, ease of processing, and eco-friendly, environmental friendly also. So coming to the potential applications, uh, I mean, even though they are less efficient, but still they are useful in many low light applications. Let's say IoT sensors. Even in indoor light or some wherever low power is uh, applicable, we can use these organic photovoltaic cells. So as I have mentioned here, so light IoT sensors, motion IoT sensors, so like this temperature IoT sensors, we can use solar cells to do this kind of multiple applications. So because of this reason, people are working hard and to develop a highly efficient and highly stable uh, solar cells. And coming to the working principle, so so as I have mentioned previously, uh, organic solar cells, uh, the main important part is active layer, photoactive layer. This photoactive layer is made of uh, uh, different organic semiconductors. One is called donor and another is acceptor. Uh, so the first process is nothing but exciton generation. As soon as light shines on the material, uh, if the incident energy is greater than the band gap of the material, it creates electron hole pair, which is nothing but exciton in the case of organic semiconductors. So this generation is nothing but exciton generation. And these excitons will be generated throughout the active layer, and they will be diffused to the interface where there is donor and acceptor interface is there. They will be diffused, and this process is nothing but exciton diffusion. And as soon as it reaches to the interface, uh, the electron prefers to lower energy level state, and a hole prefers to higher energy level state. Therefore, this will be dissociated, and this process is nothing but exciton dissociation. And as soon as this will be dissociated, this becomes a free electron and free hole, and they will be transported towards the cathode and towards anode. Electron will be towards cathode and hole will be towards anode. So this process is nothing but charge transportation. And and these charges, I mean free electron and free hole, that needs to be reached to the respective electrodes, cathode and anode. So then only this flow of electrons is nothing but current. So this will be collected at the cathode and anode. This is nothing but charge collection. The overall efficiency is a product of absorption efficiency, dissociation efficiency, and charge collection efficiency. So this is the overall. So if you want to obtain higher efficiency, we need higher absorption, higher dissociation, and higher charge collection efficiency. So this is how an organic solar cells works. This is the working principle of organic solar cells. So coming to the fabrication techniques of organic solar cells. So basically, there are two ways they can be fabricated. So one is solution process based, and the other one is vacuum based techniques. In the solution process based, there are four varieties. One is spin coating, drop casting, roll to roll processing, and inkjet printing. So here, one solvent, I mean, we need to prepare solution, and we need to coat the film. That's how solar cell will be fabricated. In the case of vacuum based system, here there is no solution at all. Only we need to take the material, powder kind of material, put it in a crucible, and put it in a vacuum chamber, and create vacuum chamber up to 5 into 10 power minus 6 millibar. Usually that is the standard pressure one need to maintain in order to get the desired thin films. So in this case, uh, I mean film will be pure, I mean will get pure thin films in the case of vacuum deposition, because of no contaminants and no I mean uh, no air molecules present within the chamber. So there are advantages with the vacuum based techniques. but when it comes to solution based techniques, here also advantages are there. I mean, this doesn't require this much costly equipment and all. So there are, I mean, these two are the techniques in order to get in order to fabricate organic solar cell. So coming to the fabrication process flow, so generally it has the complete device structure, like layer by layer structure. It consists of transport layers, electron transport layer, hole transport layer, in between the active layer, and then the top electrode, one top electrode. So first we will consider ITO coated substrate, either glass substrate or flexible substrate, and each layer will be fabricated by using either of the techniques that I am explained previously, either vacuum deposition or solution process based. So here I have taken the example of vacuum based technique, because I have used this glow box integrated with thermal evaporator and sputtering system. So this whole transport layer and electron transport layer are deposited by the thermal evaporation technique, and then active layer is by co-evaporation technique. Therefore, we can form all the layers, layer by layer structure, and then we can get the overall the fabricated device by using these techniques. So before going to do the deposition, one must do the sample preparation, like cleaning the substrate under different solutions, like that is by using ultrasonication, by using soap solution, acetone, isopropanol, and DI water for 15 minutes each. And then UV ozone cleaner, like if there are any organic contaminants present on the substrate, those things needed to be cleaned properly. So that can be done by UV ozone cleaner. So this is how the fabrication process will go. So these are the instruments that I have used for the fabrication of all the devices that I have done when I was in IT Hyderabad. So coming to the choice of the active layer materials. So what are the important parameters that we need to consider while doing the deposition? Before going to the deposition, how one need to select the materials. So we all know the sun intensity is available from 300 to 1050 nanometer. So we need to select the materials in such a way that they should absorb in this wavelength region. So those materials are only are can able to absorb and can able to convert the sunlight into electrical energy. So here you can see different materials: C60, C70, DDT, CTB, and ICBA. So these different materials can able to cover from 300 to 900 nanometer. So that is the first choice of material. And as I have mentioned in the working principle, donor and acceptor energy level alignment also one need to be considered properly, because uh, if the energy misalignment happens, suppose if it is above of this one donor, and what happens, this I mean exciton dissociation cannot happen if it is above. So that becomes loss, because this that will recombine again. So in solar cells, recombination should not happen. As soon as excitons are generated, they should be dissociated and they should reach to the respective electrodes. That contributes to the they should be able to cover the and the energy level and optimization technique. As I have mentioned here, if you see this diagram, this is the active layer. Active layer is the very important component uh, in the solar cells. So because this active layer plays a very important role, like all the photon absorption, dissociation, and reaching to the electrodes, this electron uh, hole transportation will happen from this region, this active layer. So that is the reason why this plays an important role in obtaining the higher efficiency of the solar cell. So that need to be properly optimized. If we consider two materials in the active layer, suppose let's say I have considered DT-DC-TP and ICBA. This is a donor, this is the acceptor, and we need to optimize this active layer components properly. So different thicknesses of the active layer, and then I have verified their performance parameters like open circuit voltage, short circuit current density, fill factor, and efficiency. So at 70 nanometer, it is able to give 1.59 percentage of the power conversion efficiency. So and then and not only that, whatever the donor and acceptor that we are mixing there, that needs to be like suppose 1:1.2 and 1:1.5. So like one 1% of donor and 1.5 percentage of acceptor. If you play with different concentration ratios, one can achieve higher power conversion efficiency. So in this case, I have done it for 1:1.2 and 1:1.5. At 1:1.5, 90 degrees Celsius of annealing temperature, we have obtained 3.95 percentage. And so also we have tried different other concentration ratios as well, like 1:1.8, 1:0.8, 1:0.5, so like that. So in all the cases, uh, we have obtained at 1:1.5 only, giving the highest efficiency, that is 3.95 percentage. So and we also needed to consider the annealing time and annealing temperature. These are also important parameters in order to obtain the higher power conversion efficiency of the solar cells. Like how much time I need to do the annealing of the device, annealing of the active layer, and how much temperature. Temperature also matters, like 70 degrees, 90 degrees, 120 degrees, 140 degrees. Like we need to play with these many parameters so that we will get the higher efficiency device at the end. So at 30 minutes and 90 degrees Celsius was giving the highest power conversion efficiency, that is 2.13 percentage. And we also need to consider the device active area, like whatever I'm talking about here, all about the photoactive layer. So what is the active area that one can obtain highest power conversion efficiency? So here we tried with different active areas, 1.5 millimeter by 2 millimeter, and then 1.5 millimeter by 3 millimeter. At 1.5 millimeter by 3 millimeter, 90 degrees Celsius was giving highest power conversion efficiency, that is 2.03. So these are all parameters one need to optimize in order to get the highest power conversion efficiency of the solar cell device. So once it has been done, we need to verify the uh, characterize the blend films as well as the devices. So these are the individual thin films, like donor, acceptor, and donor is absorbing from 480 to 880 around 900 nanometers, and acceptor ICBA is absorbing from lower wavelength region. So in that way, it is able to cover from 300 to 900 wavelength region. And if we mix them together, this is how it is able to cover up to 900. So there is advantage with the mixing of donor and acceptor, and it can able to form bulk heterojunction structures. So that is another thing, and we need to study the structural characterizations also, like how the blend films are formed, and what is the RMS value, and how well both uh, donor and acceptors are mixed together, and so that they can able to form the bicontinuous networks. So at 90 degrees Celsius, it is giving 2.32 nanometers, and it is able to form fine structure with the bicontinuous networks. This is the morphological characterization of blend films. And then we also need to calculate the external quantum efficiency. External quantum efficiency is nothing but the number of charges are collected for the per incident photons. So in the case of DT-DC-TB and ICBA at 1:1.5 at 90 degrees Celsius, 30 minutes annealing temperature, which was giving around 35% of external quantum efficiency. So this is how we can calculate the external quantum efficiency, and if we integrate external quantum efficiency with the unit charge, and we can obtain the current density JSC. And so then uh, we also need to identify the charge recombination dynamics. It is nothing but, suppose excitons are generating and excitons are dissociating and they are becoming free electrons and holes. Are there any recombinations present within the device, or why it is coming less efficiency? So those can be calculated by using this charge recombination dynamics. So here we can take different light intensities from 0 to 100 milliwatt per centimeter square, that is one sun. So at different light intensities, we need to calculate corresponding current density JSC and corresponding VOC, open circuit voltage. So after that, we need to calculate the slope values, uh, slope values, and then we can estimate the slope values. Based on the slope value, if it is unity, I mean 1, there are no recombinations present in the device. If it is not 1, so let's say in this case it is of at 90 degrees 1, but 70, 120, 140, it is more than 1. So that means at higher annealing temperatures, it is device is undergoing recombinations. So we should not do at higher annealing temperatures. Uh, that is the conclusion out of this one. So this is how one can estimate whether the device is undergoing recombination within the device or not. So that is the another characterization technique. So uh, in conclusion, uh, yeah. So in conclusion, we have fabricated different devices uh, with DTDC-TB ICBA and DTDC-TB C70 and DTDC-TB C60. So when we compare and see the different devices, at DTDC-TB and ICBA was giving highest power conversion efficiency, 3.95 percentage. Here JSC is also more, and VOC is also more. So this is the ultimate conclusion out of this binary structures. So coming to the, what is this? Yeah. Coming to the Turner, something is visible on my screen. Are you also seeing any this thing? Are you there, sir?
I'm seeing two red lines.
Yeah. So how to remove that one?
Actually, somebody has drawn. I think so, sir. Let me check, sir. It is not.
From where these things are coming? I do not know. Yeah. Anyway, if you get any doubt, you can note the slide number. I'll come back and explain that one. Okay. So let me continue. So coming to the ternary organic photovoltaics. So ternary is nothing but three materials in a single active layer. So if you come here and see here, here so far whatever I have done is all are binary, like two materials only. Same donor but different acceptors. In this case, for this DTTCTB and ICBA, I try to introduce the another component to the existing binary system. Therefore, it is able to cover the maximum solar spectrum, and also there is an improvement in the power consumption efficiency as well. So, uh, I have followed the same optimization techniques at 90 degrees Celsius and 120 degrees Celsius. At 90 degrees Celsius was giving the best power conversion efficiency, that is 4.68 percentage. So and so also we try to do the photophysical characteristics like absorption of the individual films and blend films, and we also try to calculate the photoluminescence spectra. So luminescence spectra is nothing but emission spectra, like with respect to donor, how the blend films are, what are the recombination dynamics here. So if you see, this is the donor and this is the these remaining things are ternary blend films, and ternary blend films are giving lower light intensity, emission intensity, meaning, so I mean not many recombinations are happening when in comparison with the donor pure film. So, and ultimately, we have tried the different concentration ratios and with different thickness. At this concentration, 1:1 to 0.5 and 150 nanometer, we could able to get 5.34 percentage. This is the highest power conversion efficiency we have achieved um, with this ternary OPV device structure. So, if you see the uh, advancement of organic photovoltaic cells from single heterojunction to quaternary, this is the advanced device structure. So, uh, from every structure, they are able to overcome the shortcomings of the previous one and try to uh, try to improve the efficiency by changing the device structure. So let me explain how these things are evolved from one structure to another structure. So coming to this structure, this is the single heterojunction. Just they considered one single donor and one single acceptor, and they put stacked together. But here only one interface is there. That's why it is single heterojunction. So in the case of bulk heterojunction, here if you see here, that means number of interfaces are increased here. So because of single interface, only fraction of excitons within the diffusion length are able to dissociate it, and rest of them are recombined. Only whichever within the diffusion length are the absorbed photons are there, those only will be able to dissociate meaning. That is the last factor. Therefore, people have come up, researchers have come up with another device structure. This is bulk heterojunction structure, and they are able to mix together, and more more donor and acceptor interfaces are available, and they can able to dissociate the number of things. And coming to the tandem structure, in this case, this is the little advanced to the binary bulk heterojunction, because in this case, um, one subcell is able to absorb one wavelength region, the other subcell is able to absorb another wavelength region. Therefore, it can able to cover the entire sun solar spectrum from 300 to 1000 nanometer. So that is the advantage. So if we stack together both of them, and we can get higher voltage and higher current uh, with this structure, tandem organic photovoltaic cells. So so this is the another advantage, but the problem is uh, fabrication of these two subcells and matching with them is another complexity, but uh, can occur here. And coming to the ternary photovoltaic cells, uh, here within a single active layer structure, uh, three materials can be uh, at a time can be deposited, and they can be uh, fabricated at a time, like co-operation technique. Either co-operation technique or solution process based technique, we can deposit all the materials at a time. So here the advantage in comparison with the tandem solar cells is recombination layer, and no need to match them together here. Uh, Deposited at a time, and there is advantage here. So suppose let's say one acceptor can be considered that will be absorbing in the lower wavelength region, and donor is in the mid wavelength region, first donor, and donor 2 is absorbing from region. So in that way, more absorption can be happened, and fabrication also becomes very easy. Here there is no need of recombination network. There is no need of matching the two networks because of the same current. Because if if we are able to connect them in series, one need to be considered the current also should match. But here in this case, no need to consider this thing. So this is the advantage with the ternary structure. And people have come up with another structure also, because uh, if they are able to incorporate another component, in this case also, they can absorb more photons, and fabrication also becomes very easy. And there is advantage, we can we have a choice in such a way that we can select energy level alignment is also can be controlled by us, and then we can uh, internal losses also can be eradicated by using these quaternary structures. So these two are emerging and in these two structures, more research is happening right now, and people are working in this research direction. So now coming to the module based solar cells. So far whatever I explained here, all are based on single cell structure. Like if you see, I have explained about the area also, device active area also, maximum of 1.5 mm by 3 mm. So it is very small device. Okay, so 1.5 mm by 3 mm means it's a very small rectangle. Small rectangle, one small rectangle can able to give 0.83 volts and 9.5 uh, milliampere current, and efficiency is 3.95% of power conversion efficiency. So But with one just 0.8 volts, let's say this one 0.7 volt, I cannot able to drive any circuit or anything with this voltage and with this current. So in order to do that one, if we are able to connect two cells in series, two cells or three cells or four cells, if we are able to incorporate series integration and parallel integration, and so that we can obtain more voltage and more current. So if you see this device structure, the purpose of this integration is in order to get higher voltages and higher current. So in this case, we have considered the 25 mm, 25 millimeter by 75 millimeter size uh, uh, ITO coated substrate, and we have done the ITO patterning. This can be done by um, clean room facility, uh, clean room facility with the lithography technique. So because these are very accurate dimensions with 1.5 millimeter by 6 millimeter. This because our device structure is 1.5 millimeter by 3 millimeter. So in order to do that one, we need to use the lithography technique to get the desired patterns, and then we can do the deposition of active layer and organic layer and silver on the. So this entire work is completely dependent on the clean room facility, lithography, as well as the uh, this thermal evaporator and glow box system. So this is we fabricated in IIT Hyderabad with this facility. First, we have done the patterning of this ITO coated glass substrate, and then we have used different deposition mask. Suppose organic layer will be deposited like only this region one needs to be deposited. This can be done by um, this can be done by uh, I mean we need to do the customized deposition mask here. So ultimately, this is the overall device structure, and this is the fabricated device. So this is able to give uh, around 4.1 volt and 1 milliampere per centimeter square current density. So this is the I mean single cell is able to give only 0.7 volt, but if we integrate them, we can able to connect more number of devices. I mean, so that we can achieve more voltage and more current and more power conversion efficiency also. So but there are still challenges are associated with this one. So ultimately this is how a module can be developed, as well as uh, this panels also will be developed. So let's say this is 75 millimeter by 25 millimeter. So if we are able to stack these kind of 75 by 25, uh, the number of series and parallel integration, we can able to achieve more voltage and more current. So this is the advantage. So ultimately, as I mentioned the topic, next generation photovoltaics for uh, today's contemporary applications. So if we stack them together like this module from single cell, cell from 1.5 millimeter by 3 millimeter to 75 by 25, and then from 75 to big scale devices, panel level, and then plant level. So we can do the um, integration of this number of devices. So ultimately, these are very relevant in today's application, in this contemporary applications, and we can use it for number of applications of the devices. So this is the, I mean, in these two structures only more advance is happening, and people are working hard to get higher efficiency solar cells. So far, 19.3 percentage efficiency was achieved with the organic photovoltaic cells, and now I am working with the quaternary this quaternary base solar cells, with aiming for more than 20% efficiency. That is our target. Um, so uh, and these can be used it for the green hydrogen production, like water splitting systems. So yeah, so these are the current trending of organic photovoltaic cells, and this is what we fabricated, and now I am working towards the green hydrogen production technology as well. So thank you for your attention, and yeah, so if anyone have any questions, you can ask me. Yeah.
Dear participants, if you have any questions, ask to sir. Sir, no one is asking questions, sir. Thank you very much, sir, for your valuable session on photovoltaic solar cells, sir.
Yeah. Thank you very much for inviting me for today's this talk. I am very happy. And if anyone has any question, you can ask, or else you can put it in chat box. I'll try to answer. Yeah.
Ratraj, sir, you can ask questions, sir. Hello.
Hello.
Yeah. Yes, sir. Continue, sir.
Sir, actually, your presentation was very nice, sir.
Yeah. Thank you, sir. Thank you very much.
We got many information about
Yeah.
LED and all, but
Yeah.
I think it is implementation part is little difficult. Yes.
Yes, sir. Fabrication, and if we are, if we are going for large scale integration, that will be difficult. Small scale devices and all, it's easy only. That optimization parts will take time. Once the optimization has been done, uh, like module level, panel level, that will be little difficult. As I shown the integration part, the number of devices, 54 cells, that connection is little tricky, bit difficult, because dimensions also very small.
Okay, sir. How the dimension measurement also you done by your own, or you have to depend to other people?
So that dimension, first it will be coming from the optimization technique that I have mentioned in the device active area. Okay, so suppose let's say I got it 1.5 millimeter by 3 millimeter. So with that active area only, we need to develop all the devices, because if we make it in another active area, it may not give the same result what I have mentioned in the previously. So for this reason, we need to follow the same device active area throughout all the 54 devices. I mean, I have mentioned it for 54 devices. So also for other device.
Sir,
Yeah.
which device is used for calculating the dimension and all, sir?
Oh, yeah. First, it is a process. Optimization, uh, it will start from thickness first. Once the thickness optimized, we'll fix the thickness and we'll move on to the donor and acceptor concentration ratios. So in what concentration ratios we need to uh, mix the two materials at a time. Like bulk heterojunction is nothing but mixing of donor and acceptor. So this donor and acceptor, we need to mix in such a way that they should give the best power conversion efficiency. So 1 is to 1.2, 1 is to 1.5, 1 is to 1.8, 1 is to 0.8, 1 is to like one we can fix it and another you can vary like that. Like
Okay,
that we need to uh, look for the active area also. uh, like from literature you will get some clue, let's say 0.045 centimeter square, let's say that is the active area. So we need to formulate in such a way that if we calculate the active area, uh, that should reflect in that active area. Let's say 1.5 mm by 3 mm. What does it mean? It is of 0.045 centimeter square. That kind of clue you will get from the literature, and we need to play with the different dimensions. Yeah.
well, sir, what are the scope of fabrication, sir?
Scope of fabrication. I mean, till now we have developed only lab scale based only. I
Okay.
mean, not in a industrial level. But if we can use this idea to implement it in a large scale, that is for sure. But it is purely based on the processing technique also. Like I have mentioned solution and uh, vacuum deposition. Vacuum is giving best, uh, I mean, best reliability. I mean, it is able to stay long time also with the vacuum based technique. So, so there is a scope uh, based on the fabrication technique and durability. Yeah.
Sir, what are the basic material used for fabrication, sir?
Okay. So, I mean, I have used all are based on fullerene based materials only, particularly acceptors. Donors, I have used small molecule based. Now I am using polymers also I am using. So different polymers are there. So I I will select the materials in such a way that they should be able to absorb sun solar photon flux. That is the ultimate thing. Yeah.
Okay, okay. Thank you for sharing, sir. Thank you.
Yeah. Thank you, sir. So
Sir,
yeah, if you have any doubt or anything, you can contact me. So my email ID also I can give it to you. So Here I'm typing my email ID.
Sir, your screen is not visible, sir. You can type it in chat box. Okay, got it, sir.
Yeah. So this is my email ID. You can send email to me if you have any questions or anything. As Dr. Ramesh previously pointed out regarding the INUP facilities here.
Yes, sir.
So these are very good actually.
Okay,
So anyone from any university can come, but you need to come up with one project proposal and some new idea.
okay, sir.
So then they will definitely give an opportunity to work here in
Okay, sir.
IIT Guwahati.
Okay, sir. Okay, sir.
Yeah.
Thank you for sharing valuable information,
Yes.
and thank you very much, sir, for your sharing your knowledge to us. It is a very nice opportunity for us.
Yeah.
Thank you very
Thank you.
much, sir.
Thank you very much.
Thank you, sir. Thank you very much, sir.
So if nothing is there, I can sign. I'm signing off.
Okay, sir. Okay, sir.
Yeah. Thank you.
Okay, sir. Thank you, sir.